Hello everyone, welcome to week 5. The goal is to finally leave graph coverage criteria and move on to other data structures and models. But before we do that, the first video for week 5 would be telling you how to solve the assignment that was uploaded for week 4. Because there was a programming question and you were asked to answer some questions about def use paths on that program. So I'd like to spend this first video for week 5 trying to see whether you have solved it and to help you if you haven't been able to solve. And you could also use this video to be able to cross check and see if your answers were right or wrong. What was the assignment? The assignment for week 4 was on design integration testing, graph coverage criteria as it was applied to design, sequencing constraints, and we also saw one problem on data flow coverage criteria. So what I'll do is I'll walk you through one question after the other in the assignment and tell you what the correct answer is and what it means, what does the correct answer mean. So the first question in that assignment was the fill in the blanks question. It asked which is the phase or stage at which integration testing sits. That means which is the phase immediately after which integration testing comes. If you remember the V model or the waterfall model that includes testing, integration testing comes immediately after unit testing. When the individual unit tested modules are ready, I'm ready to put them together and do design integration testing. So the answer to the first question would be unit testing. Second question asks, when I do integration testing, I do what is called scaffolding. If you remember the modules that we saw when we looked at classical design integration testing, it says which are the two most common types of scaffolding. The two most common types of scaffolding are test drivers and test stubs. If you remember, when we do top-down integration or bottom-up integration, I may or may not have all the modules ready. So I write a test stub when I don't have a module ready, but I want it to behave as if a module is ready. So it's like a dummy module. And when do I do a test driver? When I want a dummy module to be able to call the lower level modules, right? When I do bottom-up testing, that's when I used test drivers. So the correct answer to second question will be test stubs and test drivers. The combinations that are given here basically let you answer them in any order. You should have got full marks if you had answered them in any order or in singular or plural words. The third question asks, gives you a statement which is last def can only be from the caller back to the callee. From the caller to the callee, sorry, not back to the callee. So is it true or false? So it is obvious that it is false, right? Because even in the examples that we saw, if you remember, we saw a quadratic root example, then we saw small toy examples of just the caller-callee definitions. Last defs can also be from the callee back to the caller. So they can be in two different ways. They can be from the caller method to the callee method, and they can be given returned back, values that are returned back from the callee method back to the caller method. So this statement is false. They can be both ways. It cannot be just one way. The fourth question asks again another true or false statement. It asks whether default and implicit initializations of global variables, specifically when it comes to programs like C or Java, the programs that are written in C or Java, are they to be considered as definitions or not? Because they are implicit initializations, they are not explicitly given by the program, it doesn't mean that the values are not there, right? So they are initialized, the values are very much present. So they have to be considered as definitions even though they are not explicitly present as statements in the program. So the answer to this question is true. Default and implicit initializations of global variables should be considered as definitions while working with data flow criteria. The fifth question was a fill in the blank question. It asks you, while you're testing for sequencing constraints, how do we write typically the TR or the test requirements for? If you remember, we looked at this file ADT example, and then that file ADT example had a few methods that it was exposing, right? Open a file, read a file, write a file, close a file, right? So typically we write test requirements to violate the sequencing constraint so that we can flag it as an error. So the answer to this fill in the blank question is violate. From question 6 onwards, in the fourth assignment, you were given a program that was computing the square root. The program was given without any loops, but it had a loop. In fact, it had more than one loop in the form of go-to statements. I have taken this program from the classical paper by Sandra Raps and Elaine Bayukar 1982 paper, which I gave you as a reference for data flow testing. Right? This program is from that paper. And there were a few questions about that program, specifically related to data flow coverage criteria. So what was the program doing? The program was trying to compute square root of p, where p was this number, up to some kind of allowed accuracy. And it's a classical algorithm by this Wensley. If you can Google for it and check, it uses what is called a divide and conquer approach. It tries to look at first look at the interval 0 to p and try to see where the square root of p could be. Will it be in the first half or will it be in the second half? And based on what it says, it breaks the interval into two halves, repeats this procedure again, breaks the next interval into two halves, repeats this procedure again, and it narrows down the interval where square root of p comes. And when it finally terminates and it outputs a value that's almost the square root of p, modulo a small difference in accuracy. Right? So here is the code of the program, written specifically in a long way that helps you to learn also how to draw control flow graphs. As I told you, the program has while loops, not as while loops or for loops. It has them as go-to statements. So here I begin, I read the numbers, I do a set of initializations, and then I say if this number is greater than or equal to 2, then you go to 18. 18 means I can't find square root, print error. And it says if the number is less than or equal to e, go to 16. 16 says I have found the square root, print it. Right? So then where is the loop? The loop is around here. So there is a if statement here. It computes d and t. If t is less than 0, it says go to 14. 14 does 2 stars t, c, and then it says go back to 7. So you do this, then you could either go to 16 or you continue 8, 9, 10, 14 and go back to 7. So there is a loop here. So what was the question about? The question was about, first it asked you to draw a CFG. There were no marks allotted to drawing of the CFG, but the questions that were to follow were based on the CFG, especially 4 of those questions. The first one wasn't. The later questions were based on those of drawing the CFG. And because this program has a lot of statements and the questions were based on paths in the CFG, I had also given you some guidelines on how to label the vertices of your CFG. So these are the guidelines. So what it says is that the first node in your CFG, call it node 1, should be one node that represents this bunch of statements that are in one after the other, 2, 3, 4 and 5. So we'll go back to the program. Statement 2, read PE, 3, this statement d is equal to 1, 4, x is equal to 0, 5, c is equal to 2 star p. All this at the beginning of the program will be node 1 in the CFG. That's what was given here. And node 1 also includes this first decision statement at line number 6. Then there is a branching into node 2 and some other node. And in node 2, the second decision statement comes, which means this decision statement is false, right? Second decision statement comes, and then d by 2, t and so on. That is node 3, which is statements 8 and 9, node 3 in the CFG, and so on, right? So here is how the CFG will look like if you had made an attempt to draw it using pen and paper. So node 1 represented was the initial node of the program where the program computation begins. It represents these 4 statements. Read PE, d is equal to 1, x assigned to 0, c is 2 star, which are these 4 statements. And it also represents the decision. If the if statement turns out to be true, that is if c is greater than or equal to 2, if c is greater than or equal to 2, go to 18. 18 says print error. So in the CFG, you go to some node, call it 6, as per the convention that I had given you to do in the question, which is labeled with the statement print error. Otherwise, you go to statement node 2 in the CFG, which is the next if statement, d is less than or equal to e. So what you do here, if d is less than or equal to e, then you print x. Go back to the code. If d is less than or equal to e, go to 16. 16 says print x. right? Otherwise D is greater than E, you come here, D is equal to D by 2, statements 8, 9, 10. So D is equal to D by 2, statement 8, T is equal to C minus 2 into X plus D, statement 9, and the decision at 10 is also modeled here. Decision could be positive or negative. It checks if T is less than 0. If T is less than 0, it asks you to go to 14, where you do C is equal to 2 star C. If T is less than 0, then you do C is equal to 2 star C, and then what you do, you go back to 7, which is node 2 for us. If T is greater or equal to 0, then you do 2 more statements and then you go back to 7. So these are the loops that I was telling you that the program has, right? Divides the number by 2, checks the range of the square root, takes the first half of the second half based on where the square root, it keeps doing it till it reaches a value that is approximately the same as that of the square root. But these loops that you find in the CFG are not directly given as while statements or for statements in the program. They are given in terms of go-tos. So I hope you all could get a CFG that looks somewhat like this. Even if it was not drawn like this, your CFG should have had 7 nodes, and there should have been 3 decision points. The point 1 here, point 2 here, point 3 here, corresponding to 3 if statements that were in the code. 1 here, 1 here, and 1 here. And these go-tos tell you to loop back, and that's what we have done here. The go-tos loop back correctly. Please don't get confused with the numbers 1, 2, 3, 4 that you find in the nodes here with the statement numbers of the program. These are different. They don't mean the same. So when I say go to 7 here, I mean go to statement number 7 in the program. Statement number 7 in the program is actually node number 2 in the CFG. So please don't mix up these two. So once you have drawn the CFG, you should be able to answer most of the questions that were asked. So now we'll look at one question after the other and see what were the questions that were asked. So the first question, in fact, was not dependent on the CFG. It just asks you to look at the program, to study the program, and find out on your own without resorting to any graph-based testing or any other testing, does this program have an error? We typically give this kind of questions in a testing course to help you to appreciate that the goal of a tester is to be able to find an error. So if you had done this, if you just studied the program and understood what it was doing with reference to the divide and conquer algorithm, you will realize that the program did have an error. The error in the program was the order in which statements 11 and 12 were given to you got interchanged. It should first compute this value, only then can it increment or reset the interval value of x. But the program was first incrementing x and then computing c. It will miss computing certain values of the square. So you take a small enough number and let the program go through it, you will realize that the statements 11 and 12 should be interchanged. So that is the error in the program. This program does have an error. So the rest of the questions are aimed at helping you to understand data flow coverage, and specifically can we use any of the data flow coverage criteria that we saw to find this error, the error that says that statements 11 and 12 were indeed interchanged. So the second question was, does the set of test paths 1, 6, 1, 2, 3, 4, 2, 3, 5, 2, 7 satisfy edge coverage? So please remember these test paths 1, 6, and then 1, 2, 3, 4, 2, 3, 5, 2, 7. We'll go back to the CFG 1, 6, and then 1, 2, 3, 4, 2, 3, 5, and then 7. Does this satisfy edge coverage? Yes, it does, right? Because 1, 6 covers this edge. Then 1, 2, 3, we've covered these 3 edges. 4, this edge is also done. 2, 3 once again, but we've already covered it, doesn't matter. 5, 3, 5, then 5, 2, and 2, 7. So the answer to that question is yes, it does satisfy edge coverage. In fact, it covers the edge 2, 3 twice, but that doesn't matter. It visits every edge exactly once. The second question gives you a set of test paths, a lot of them in fact, and it asks you, lists 3 coverage criteria and asks you which amongst these 3 coverage criteria are satisfied by this test path. So if you see the test paths, before looking at these test paths, let's go and look at the control flow graph. As I told you, right? Control flow graph has how many branches? There's one branch here, there's one branch here, and one branch here, corresponding to the 3 if statements. The third if statement had go-tos, so it was like having a loop back. So if I want to do edge coverage or any kind of coverage, I should cover this 1-6 separately because it's a standalone path, and then I can do all these, right? So these paths that are given here do 1-6 separately, and then they had this one which we saw in the last question about edge coverage, and then it had 1-2-7. So let's go back and see what 1-2-7 is. 1-2-7. So 1-2-3 took this branch, 1-2-7 took this branch. Fine. So we seem to be doing fine. And then what else is there? Then it's the same thing as this path. The fourth path is very similar to the second path. What is the difference? The only difference is that 1, 2, 3, 5 here, 1, 2, 3, 4. So let's see what does that do. 1, 2, 3, 4, 2, 3. Right? So it does cover this part of the second decision statement, and similarly this covers the other half of the second decision statement through 4, and this covers the other half of the second decision statement through 5. So the question that was asked was, which coverage criteria does it use? All defs, all uses, or all DU paths? The correct answer is that it does all uses coverage. You could have also said all defs coverage, but please remember all uses coverage subsumes all def coverage. So we are looking for the stronger option here. The stronger correct answer is all uses coverage. So if you had written all defs coverage, then marks would not have been given unless you had written all uses coverage as your answer. It doesn't cover all DU paths. Can you tell me which is the DU path that it is going to leave out? It will be good to look at this control flow graph and help yourself by understanding which is the DU path that is left out, and why do these set of test paths not satisfy all DU paths coverage. Please do that as a small little self-check for yourself. So the correct answer to this question would be all uses coverage. The next question tells you that there is a definition of C in node 5. So we'll go back to the control flow graph and see. Is there a definition of C in node 5? Yes, because C is done given this assignment statement. So C is defined. Then it asks you to find out where is C used. How will C be used? The only way to use C would be to go out of 5, and the only way to go out of 5 would be to go back to 2. So once I go back to 2, I have a choice. I could go to 7 or I could go to 3. But my goal is to be able to see this definition of C, where was it used? That was the specific question about. So from 5, I go back to 2, and suppose I take the path 2, 7. Clearly this path doesn't result in the use of C, because the use of this edge are D and E, and the use of this vertex 7 is X. So this doesn't help for that. And suppose I take 3, if you see, C is used here to define T. A correct answer to that question would be the definition of C will result in a use if the path 5, 2, 3 is included. You have to be able to do 5, 2 and then go to 3. Is that clear? So the next question again gives you a whole set of paths, and it asks you which is the coverage criteria that it satisfies. A simple answer to this question would be branch coverage. You could have also written decision coverage. That would have also been correct. Why does it cover branch coverage? Because if you see this set of paths nicely there are 3 branches corresponding to 3 if statements, and these set of paths precisely take those branches. This path takes the first branch 1, 6. Then these are the paths out of the second branch 1, 6 and 1, 2. And in 1, 2 you could do 1, 2, 3 or 1, 2, 7, which are the 2 options. And in 3 you could do 1, 2, 3, 4 or 1, 2, 3, 5. Right? So if we'll go back to the CFG for a minute. So I do 1, 6 or 1, 2. And then at 2 I have a choice 1, 2, 7 or 1, 2, 3 for the 2 branches. And then at 3 I have a choice 1, 2, 3, 4 or 1, 2, 3, 5. So all possible branches are listed here, and the set of paths that this coverage criteria satisfy would be branch coverage or decision coverage. You should have got full marks if you had written either of these options. So I hope this assignment helped you to understand how to look at simple programs, draw their control flow graphs, annotate it with defs and uses, and compute data flow and structural coverage criteria over them. What we will do from next lecture onwards would be to look at logical predicates, coverage criteria over logical predicates, and read out this exercise all over again. Take source code, see how logic applies to source code. Take specification, see how logic applies to specification, and so on. Thank you.